As the Cold War raged in the mid-20th century, the global powers of the United States of America and the USSR spent considerable money and energy developing weapons to annihilate one another at a moment's notice. The demand for intercontinental nuclear missiles was unprecedented. In the 60s and 70s, it was revealed that at the height of the war, the US had 1,710 ballistic missiles ready for launch, both from land and from submarines. But launching long-distance projectiles capable of mass destruction is nothing new. If we turn the clocks back to March 1918, we stumble across what was labeled the Paris gun. Weighing 256 tons and with a barrel length of 21 meters, it was able to shoot a 211mm projectile over a range of 130 kilometers. This was by far the highest point ever reached by a man-made object, so high that gunners, in calculating where the shells would land, had to take into account the rotation of the Earth. For the first time in warfare, deadly projectiles rained down on civilians from the stratosphere. Impressive as it is, there was nothing at the time that could make such a weapon precise enough to be strategically effective. The projectiles of this behemoth very rarely hit the desired target. Even a city as big as Paris was too small of a target to fire from that range. With only a 45-year difference, the missiles of the Cold War had an operational range of 8,900 kilometers, and were able to frequently hit precise targets. But what allowed such a projectile carrying a 1 megaton warhead to be so effective while being fired from so far away? Guidance. The Minuteman I intercontinental ballistic missile started its development in the 1950s, and is named after the colonial Minutemen of the American Revolutionary War. This is because it used solid fuel for propulsion, which, in contrast to liquid fuel that needed to be filled every time before flight, meant that it could be ready to launch at a minute's notice. This also allowed the rocket to be stored away for long periods of time. At a unit cost of approximately $7 million for the latest missiles, this piece of engineering combined the raw resources and technological capabilities of the post-war United States with complex circuitry and hardware all being controlled by one central computer, the D-17B. Weighing 28 kilograms and having the dimensions of 20 by 29 by 5 inches. This computer contained 1,521 transistors, 6,282 diodes, 1,116 capacitors, and 504 resistors. It was designed and built by Autonetics, a division of North American Aviation, later a division of Boeing. The Minuteman I missile used an inertial navigation system, or INS, which used accelerometers and gyroscopes to calculate the trajectory of a rocket without the need of external references. This is what the computer received as input. The strict requirements of this weapon system meant that the D-17B computer needed a high degree of reliability and ruggedness to withstand the unstable conditions of exiting and re-entering Earth's atmosphere. This was achieved using solid-state electronics, which simply means that the electronics were designed with semiconductor equipment, such as transistors, diodes, and integrated circuits. The design was also kept simple to minimize the breaking points of the computer. When the D-17B was designed in the late 1950s, transistors significantly lacked reliability compared to today's computers, and reliability in a system like this was key. This is why diodes significantly outnumbered transistors, as a simpler diode-resistor logic was implemented over the conventional diode-transistor logic, though transistors were still used where they were absolutely necessary. Reliability was further enhanced by using rotating disk memory, where a read operation did not erase the data from where it was reading. This is called non-destructive readout, or NDRO. All of these reliability measures proved to be effective, as the Minuteman missiles achieved a mean time between failures of over 5.5 years. The capabilities of the D-17B computer were very primitive. It obviously used a binary number system with a 2's complement representation of negative numbers. This simply means that in order to change a binary number from being positive to negative, the bits of the number needed to be inverted and incremented by 1 to achieve negativity. A voltage reading of 0 volts would result in a 0 or false, and a voltage reading of minus 10 volts would result in a 1 or true. In computer science, a word is a fixed size piece of data that is handled as a unit by the processor. In this case, the D17B used 11 bits to store data words, and 24 bits to store instruction words. 24 bits were also used for data when double precision was necessary. In total, its word length was 27 bits, as the remaining 3 were used as spare and synchronizing bits. But how fast could the D17B execute mathematical operations? Adding two numbers would take 78 and 1/8 microseconds, while multiplying would take 546 and 7/8 microseconds, or 1015 and 5/8 microseconds if double precision was used for the operands. Any division operation would have to be done in software, as this computer had no such functionality. The D17B had more instruction capabilities than just arithmetic operations though, as its instruction set consisted of 39 total operations from a 4-bit operation code, ranging from shifting bits to voltage output. The operation code is simply a binary number that sets a numeric label to every instruction so that the processor knows which operation to do. Therefore, all software on this computer was written in assembly, where registers and memory are directly manipulated using the instruction set of the processor. The final clock speed of the D17B, 345.6 kHz. The final cost of the D17B, $250,000. As a few years passed and the height of the Cold War raged, both the US and the USSR continued to upgrade their arsenal of nuclear weapons. The Minuteman project was no different. A few years later, in 1964, the Minuteman II ICBM was developed, which had an improved range of 10,200 kilometers and an accuracy of 1 mile. This was mainly due to the fact that it included a new computer to control guidance, the D37C. At face value, the D17B and D37C did not differ much. Both were serial, synchronous computers that used 2's complement binary numbers. Both used 11 and 24-bit words for data and instructions respectively, and had the same execution times for addition and multiplication, as well as the same clock frequency of 345.6 kHz. However, naturally, there were notable improvements over the last generation. Most notably, that the instruction set now contained 57 instructions, compared to the D17B's 39. Division was now also possible on the computer's hardware, which took on average 2 milliseconds to execute. The dimensions were also significantly improved, going from 20 by 29 by 5 inches to 20.9 by 6.9 by 9.5 inches. This was due in part to the increased use of integrated circuits developed by Texas Instruments, the same company which is now responsible for developing TI graphing calculators. The final cost of the D37C proved to be less expensive than its predecessor, costing only $139,000 per unit. The mean time between failures has remained classified. Not much is known about the Minuteman III missile, seeing as this missile is being used today and even earlier models are planned to operate until 2030, the specifications of their guidance system computers are much less verbose. What is known is that the early Minuteman III ICBMs were equipped with the Autonetics D37D computer, which boasted more disk memory and overall enhanced capability over its two predecessors, later being replaced by a 16-bit, high-speed microprocessor chipset.
What I have for you is microprocessors.
In 1993, the Guidance Replacement Program was launched to replace the old generation flight computers with something more high-speed and modern. Since the 2010s, more than $7 billion have been spent to upgrade the existing 450 Minuteman III missiles in the US arsenal. These ICBMs are currently contracted out to Boeing for development, and if we want to know more about the computer hardware under the nose of these missiles, we might just have to wait a few more decades. All we know is that the incorporation of current age technology in the guidance system of these missiles with each generation has resulted in smaller, more capable, and less vulnerable weapons to potentially cause Armageddon. With all the technology available to us in the modern world, it's hard to imagine such a dangerous weapon system being guided towards its target using such primitive computation capabilities. Whether we use such a technology to send people to the moon and other planets, or we use it to annihilate one another and destroy our only planet, is up to us. One thing is for sure, the computers used in ICBMs across different nations use software that is directly written to the disk of the computer. Once the missile is launched, the guidance system cannot be changed or affected from the ground. This is a feature to prevent the enemy from interfering in the planned trajectory of the missile. In other words, once the launch button has been pressed, there is no going back. Our fates are sealed.